Hello, this is Stefan again from schristoph.online. Today we'll talk about my latest blog post, the third in my complexity theory series. This one is about the P versus NP asymmetry. Hard to find, easy to check. That same asymmetry, it turns out, is quietly one of the load-bearing ideas behind how we get more out of AI reasoning models. The Clay Mathematics Institute states it in one sentence. If it is easy to check that a solution is correct, is it also easy to solve the problem? Their example is picking 100 compatible students from 400 applicants. Checking a proposed list against the forbidden pairs is trivial. Generating a valid list from scratch is the hard part. That gap, unproven since 1971, is the asymmetry. This diagram is the whole idea in one picture. For a hard instance, finding a solution has no known efficient algorithm, while checking a proposed one is cheap and polynomial. Solving is hard, checking is easy. Keep that shape in mind, because three familiar AI patterns are just this asymmetry in disguise. But first, a guardrail, because this is where overclaiming starts. Do language models solve NP-hard problems? No. They heuristically search a space of candidate answers and sometimes find good ones. The verification is cheap intuition is a lens for why certain patterns pay off, not a claim that a model has cracked an intractable class. Carry the asymmetry into AI, and three familiar patterns line up as the same idea. Test time compute is the search half. Spend more inference effort on hard prompts. Verifiers are the check half. A separate, often much smaller model or a deterministic test scores candidates and picks the good ones. And an agent loop combines them, propose an NP-style guess, then confirm it with a P-style check and iterate on what fails. Why is this such a good deal? If checking is genuinely cheaper than generating, a small reliable verifier in front of a strong generator can raise quality for less added compute than making the generator bigger. Whether it also lowers your dollar cost and latency is a separate question. Because extra samples add tokens and wall clock time, so treat cheaper as something to measure end-to-end. Here is the loop. A strong generator proposes a candidate to a cheap verifier, a smaller model, a test, or a tool. Accept ends the loop, reject sends it back. Gating a strong generator with a cheap checker is often cheaper on compute than simply scaling the generator, with the bill and latency measured separately. The evidence sounds almost too good. So reader rightly asks, is it cherry-picked? It is real and carefully bounded. In a compute match comparison, a smaller model with test time search beat a model roughly 14 times its size, but only on problems where the smaller model already had a non-trivial success rate. The qualifier is the whole point. Search amplifies a model that can already sometimes get there. It does not conjure capability from nothing. Complexity theory also warns you where the trick stops working. The checker has to be cheap and reliable, or the asymmetry collapses and you pay twice. Not everything is cleanly verifiable, so open-ended writing and taste are weak spots, while code and math shine. And a wrong verifier is worse than none, because a checker that confidently accepts bad answers actively steers the search towards them. So how does this land on AWS, generate and verify maps directly onto how you compose models on Amazon Bedrock? A strong model as the generator and a cheaper model or a deterministic check in the verifier seat. The retry against a cheap judge loop is application logic you write around those calls, not a single switch. The win is architectural, and whether a given verifier earns its place is a measurement question against your task and latency budget. This is the primary source for the theory. The Clay Mathematics Institute's statement of the P versus NP problem, one of the 7 Millennium Prize problems, it is where the easy to check versus easy to solve framing and the compatible students example come from, worth seeing in its original form. And this is the source for the striking result. The paper by Snell and colleagues on scaling test time compute optimally. This is where the compute match comparison and the smaller model beats a 14 times larger one finding come from, along with the honest boundary that search amplifies existing capability rather than creating it. Thanks for listening. I hope this was helpful. If so, you can reach out on LinkedIn directly or head to my blog at schristoph.online. Let's keep in touch. Take care.